The night slows down in small ways. Your breathing evens out. The room settles into its own temperature. And somewhere, maybe on a table near you, a cup of tea is cooling. Welcome to the Sleepy Physicist. This is a place where physics moves slowly enough to rest inside. If you find something here that helps you sleep, a like or subscribe helps others find this quiet too. Tonight, we're going to sit with something that happens so often you've stopped noticing it. The way warmth leaves. The way it never comes back. The tea was hot a few minutes ago. You could feel it through the ceramic. Now it's warm. Soon it will match the air around it. The heat didn't disappear. Physics doesn't allow that. Energy can't vanish. It just moves. When the tea was hot, the molecules inside were vibrating fast. Faster than the molecules in the air. Faster than the molecules in the cup itself. And when fast-moving things touch slow-moving things, something transfers. The heat moves outward. Into the ceramic first, then into the air touching the surface, then into the table beneath. It spreads. You can feel this if you hold your hand near the cup. The air just above it is warmer. Not hot, just warmer than the air a foot away. That warmth is the tea's energy, now residing in air molecules. They're moving a little faster because of it, bouncing into each other, drifting upwards slightly. The room is large compared to the cup. The air has volume. The walls, the floor, the ceiling, all of it can absorb tiny amounts of heat without changing temperature noticeably. So the tea's warmth dissolves. It doesn't concentrate anywhere. This is what makes the process irreversible. Not that the energy is gone, but that it's now distributed across so many molecules, in so many directions, that there's no way for it to gather itself back into the cup. Imagine trying to collect all the air molecules that were warmed. They've already bumped into other molecules. Those molecules bumped into others. The energy has been handed off, again and again, into a network too vast to reverse. The tea doesn't know where its heat went. The room doesn't remember which molecules received it first. The transfer leaves no map. You could, in theory, add energy back to the tea. You could reheat it. But that's not the same as reversing what happened. That's introducing new energy, from a stove or a microwave, to replace what was lost. The original heat? The specific energy that left the cup in the last 10 minutes? That's gone into the room. Permanently. This is happening everywhere. All the time. Your skin is warmer than the air, so you're losing heat to the room right now. Your phone. Your pillow. Anything warmer than its surroundings is cooling. And nothing cools in reverse. There's no moment where the air decides to give its energy back. No instant where the table returns the heat it absorbed. The transfer only goes one way. Warm to cool. Never cool to warm. Not on its own. This one-way movement has a name in physics. It's part of something called entropy. But you don't need the name to feel the truth of it. You've watched ice melt. You've never watched water freeze itself without a freezer. You've seen coffee cool. You've never seen it heat itself back up. The universe allows energy to spread. It does not allow energy to spontaneously gather. The tea will keep cooling until it matches the room. And then, nothing will happen. The molecules in the tea and the molecules in the air will have the same average energy. They'll still be moving, still vibrating, but there will be no difference left to drive any change. That's equilibrium, the end point of every thermal process. The place where everything arrives and nothing leaves. You can delay it. You can insulate the cup. Wrap it in cloth. Put a lid on it. But even then, the heat will find its way out. Slowly. Inevitably. Because the room is patient. And the room is large. What's strange is how familiar this feels. How expected. Of course the tea cools. Of course the warmth fades. It would be startling if it didn't. But that expectation, that sense of obviousness, is actually you sensing one of the deepest patterns in physics. The direction that energy flows when left alone. Toward dispersal. Toward distribution. Toward a state where it spreads so thinly, so evenly, that it can't do anything anymore. The tea's heat could have moved a small turbine if captured correctly. It could have generated a tiny voltage. But once it's in the air, scattered across 1,000,000 trillion molecules, it's no longer available for work. It just exists. The energy is still there. Still conserved. The total amount in the room hasn't changed, but its usefulness has. And that's what's really leaving when the tea cools. Not the energy itself, but the concentration, the difference, the potential. This will keep happening. Not just to tea, to stars, to galaxies, to the universe itself. Everything warm is cooling. Everything concentrated is spreading. And none of it, not once, flows backward on its own. The tea will be room temperature soon, and when it is, it will stop changing. Not because it's out of energy, but because there's nowhere left for that energy to go. It will have arrived, and it will rest there. Just like the night. Just like you. A pendulum swings in an empty room. Back and forth. Each arc a little shorter than the one before. You've seen this. Maybe in an old clock. Maybe in a physics classroom. The bob moves through air, tracing the same path, but never reaching the same height twice. It starts with a push. Someone pulls it to one side and lets go. Gravity takes over. The bob falls, gaining speed, passing through the lowest point and climbing the other side. For a moment it seems like it might return to where it started. But it doesn't. It stops just slightly lower. Where did the motion go? Not into the string. The string is just holding tension. Not into the pivot point, though there's friction there. Most of it went into the air. As the pendulum moves, it pushes air molecules out of the way. Those molecules were sitting still, or at least moving randomly. Now they're moving in the direction the pendulum shoved them. The bob transfers some of its energy to them. Not much. Just a tiny amount with each swing. But over time, it adds up. The air molecules don't stay pushed for long. They collide with others. They bounce. They distribute the energy they received into even more collisions. Within seconds, the motion that was in the pendulum is now in thousands of molecules. Within minutes, millions. The pendulum doesn't know this is happening. It just knows it's slowing down. Each swing takes the same amount of time, but covers less distance. The arc tightens, and eventually, it stops. But the energy didn't stop. It just stopped being visible. When the pendulum was swinging, you could point to it. You could say, "There's the motion. I can see it." But once it stops, the energy is still in the room, just not as movement you can track. It's in the air now. Thermal motion. The random jittering of molecules that we call heat. If you had an impossibly sensitive thermometer, you could measure it. The air in the room is now slightly warmer than it was before the pendulum started swinging. Not by much. A fraction of a degree. But the energy is accounted for. It didn't vanish. It transformed. From organized motion, back and forth, predictable, visible, into disorganized motion, random, scattered. This is the same process as the tea cooling, but in reverse order. The tea had disorganized energy, heat, and it spread into the room. The pendulum had organized energy, motion, and it also spread into the room. Both ended the same way. Dispersed. Blended into the background. You could restart the pendulum, give it another push. But that doesn't undo what happened. That's new energy, from your hand, from your muscles, from the food you ate. The original motion? The specific kinetic energy the pendulum had 5 minutes ago. That's gone. Not destroyed, but no longer motion. This transformation happens everywhere. A car brakes. The kinetic energy of the car becomes heat in the brake pads. A ball bounces and eventually stops. The energy becomes sound, heat, vibration in the ground. Friction is the name we give to this process. But friction isn't really a force that destroys energy. It's just the name for all the tiny interactions, all the microscopic collisions that turn visible motion into invisible motion. Rub your hands together. They warm up. The motion of your hands, sliding against each other, becomes motion in the molecules of your skin. You can feel the transformation happening. The pendulum can't feel it, but it's the same process. Over longer timescales, this transformation is everywhere. A river flows. Its motion becomes heat where it rubs against rocks. A planet rotates. Its spin very slowly decreases as tidal forces turn that rotation into heat in the ocean. The moon is moving away from Earth, not because something is pushing it, but because the Earth's rotation is slowing and the energy has to go somewhere. It goes into the moon's orbit. Motion doesn't disappear. It relocates. It converts. It becomes something else. But once it becomes heat, once it scatters into random molecular motion, it's very hard to turn it back into organized motion. Not impossible, but hard. You'd need a machine, an engine, something that could gather the scattered energy, concentrate it, and redirect it. But even that machine would generate more heat in the process, more than it recovers. So the total scatter always increases. The pendulum doesn't care about this. It just swings until it doesn't. The air doesn't care either. It just accepts the energy and redistributes it. But the universe keeps a record. Not in a ledger, not in some cosmic accountant's notebook, but in the state of things. The pendulum's stillness is the record. The air's warmth is the record. The fact that the motion is now untraceable, spread across so many molecules in so many directions, is the record. You can't rewind it. You can't ask the air to give the motion back. The air doesn't remember which direction to push. And even if you could somehow organize every single molecule, align them perfectly, synchronize their movements, the energy required to do that, the work it would take, would generate even more heat somewhere else. The pendulum rests. The motion is gone from where you can see it. but the energy remains. Just transformed. Just redistributed. Just hidden in the jittering of invisible things. And that's what motion becomes. Not absence, not loss. Memory. Written in warmth. There are things in the universe that flow easily, and things that refuse to flow at all. Water runs downhill without hesitation, pulled by gravity toward lower ground, and you don't need to convince it, or help it, or wonder why. It simply goes. Heat is like this too, but only in one direction. If you place something warm next to something cool, the heat will move from the warm object into the cool one, crossing the space between them through contact or through air, spreading outward in a way that feels inevitable. You expect this. You've seen it your entire life. But heat will not flow the other way. Not without help. A cold glass of water sits on a table in a warm room, and the room's heat flows into the glass, raising its temperature degree by degree until the water matches the air around it. But the glass will never spontaneously pull heat from the water and send it into the room to make itself colder while the room grows warmer. That doesn't happen. Ever. And this refusal is not a small detail. It's one of the deepest asymmetries in nature. You can push a boulder uphill if you're strong enough, working against gravity, expending effort to move mass from low elevation to high elevation, and the boulder will stay there once you've placed it at the top. Gravity doesn't care which direction you move things, as long as you supply the energy to fight it. But heat is different. Heat will not climb on its own. It will not gather itself from a cool place and move into a warm place without something forcing it to do so. This is not because heat is lazy or because the universe has preferences. It's because of how energy disperses when left alone. When a warm object touches a cool object, the molecules in the warm object are moving faster, vibrating with more energy, and when they collide with the slower molecules in the cool object, they transfer some of that motion. Fast molecules slow down slightly, and slow molecules speed up slightly, and over many billions of collisions, the energy evens out. The process is statistical. Not every collision transfers energy in the expected direction, but the overwhelming majority do, simply because there are more ways for energy to spread than there are ways for energy to concentrate. The math favours dispersal. Imagine a room with all the fast-moving air molecules on one side and all the slow-moving molecules on the other. That's an organised state, a rare configuration. The molecules won't stay that way for long because as they bounce around they'll mix, and once they're mixed, the chances of them spontaneously separating again are astronomically small. Not impossible. Just so unlikely that you would never see it happen, even if you watched for billions of years. Heat flowing from cold to hot would require that kind of spontaneous organisation. It would require slower molecules to collectively give their energy to faster molecules, concentrating motion in one place while creating a deficit in another. And while individual molecules might do this in isolated collisions, the overall trend never reverses. The collective behaviour always moves toward mixture. This is why your refrigerator needs to be plugged in. It doesn't cool your food by asking heat to flow from cold to hot. It forces heat to move in that direction by doing work, by running a compressor that uses electrical energy to pump heat from the inside of the fridge to the outside. And in doing so, it generates even more heat in the coils on the back of the appliance than it removes from inside. The total disorder increases. Always. You could theoretically build a perfect insulated box that prevents any heat from entering or leaving, and if you place something warm and something cool inside that box, the heat would still flow from warm to cool until both objects reach the same temperature. The box doesn't stop the process, it just isolates it. And once the objects are the same temperature, nothing else happens. The energy is still there, distributed evenly between them, but there's no difference left to drive any further change. No flow. No movement of heat. This endpoint is inevitable for every isolated system. Two objects in contact will always equilibrate. The warm one will cool, and the cool one will warm, and they will meet somewhere in the middle and stop. The universe does this too, but on a much longer timescale. Stars radiate heat into the cold vacuum of space, pouring energy outward in every direction, and that energy spreads thinner and thinner as it travels. Galaxies glow. Gas clouds collapse and heat up, and then radiate that heat away again. Everything warm is losing heat to everything cool. And because the universe is expanding, the cool parts are growing, the distances are increasing, and the heat has more and more space to spread into. Eventually, after an unimaginable span of time, every star will burn out, and every warm object will cool, and the entire cosmos will settle into the same temperature. Cold. Dark. Still. Not because the energy is gone, but because it spreads so evenly that there are no differences left. No hot and cold. No flow. Heat's refusal to climb is what prevents the universe from rewinding. If heat could spontaneously flow from cold to hot, then the evening out process could reverse. Stars could reignite by pulling energy from empty space, and time itself would lose its direction. But that doesn't happen. Not here. Not anywhere we've ever observed. The flow is one way. Always downhill in terms of temperature. Always from concentrated to dispersed. You feel this when you step outside on a cold morning, and the heat from your skin flows into the air, making your face sting and your fingers numb. Your body is warmer than the air, so the heat leaves. The air doesn't give it back. You can warm yourself again by going inside, by standing near a heater, by drinking something hot. But that's not the air reversing its flow. That's new heat being introduced from another source. The original heat that left your skin is now part of the cold morning air, mixed into it, diluted beyond recovery. Gone in the only way energy can be gone. Not destroyed. Just spread too thin to gather, and so heat falls. It flows downhill. It moves from where there's more to where there's less. And it will never climb back up. Not on its own. Imagine the longest wait. Not the kind measured in hours or days or even lifetimes. The kind that stretches past the existence of stars, past the formation of galaxies, past everything you could witness or record or remember. A wait so long that waiting stops meaning anything. That's where the universe is headed. Right now, tonight, as you lie here listening, the cosmos is full of difference. Hot stars burning in cold space. Dense planets orbiting through near vacuum. Pockets of intense energy scattered across vast stretches of almost nothing. And all of it is evening out. Every star that shines is pouring light into the darkness around it, sending photons outward in every direction, never to return. Those photons carry energy away from the star and into space. They spread. They thin. They cool as the universe expands beneath them. The star doesn't get that energy back. It just keeps giving. And eventually, after billions or trillions of years depending on the star's size, it runs out of fuel. The fusion stops. The core collapses or disperses. The light fades. One less source of heat in the universe. This is happening to every star. Not all at once. Some will burn for trillions of years still. Small red dwarfs, sipping their fuel slowly, glowing faintly. But even they will eventually dim. And when the last star goes out, when the last bit of fusion ends, and the last photon radiates away into the expanding void, the universe will be darker than it's ever been. Colder than it's ever been. But not empty. Not silent. There will still be objects. Dead stars. Black holes. Planets no longer warmed by anything. Gas clouds too thin to collapse. All of it drifting through space, losing heat. because even a cold object radiates. Slowly. Imperceptibly. But it does. Everything above absolute zero emits thermal radiation, photons leaking away from the object's surface, carrying tiny amounts of energy into the surrounding space. A planet that's already frozen will grow colder still. A dead star will cool further. And as they radiate, the space around them doesn't warm. It can't. The universe is too large now, too spread out. The energy just dissolves into it. You can picture this if you shrink it down. Imagine a single warm stone in the center of an infinite dark room. The stone radiates heat. The air around it warms slightly. But the room has no walls. It goes on forever. The heat from the stone spreads outward, carried by air or radiation, and it never accumulates anywhere, because there's always more room for it to spread into. The stone cools. The room doesn't warm. That's the universe. The room with no walls. Trillions of years from now, everything will have radiated away as much heat as it can. Black holes will evaporate through Hawking radiation, a quantum process so slow it makes stellar lifetimes look like seconds. They'll leak particles and energy until nothing remains but faint radiation dispersed across unimaginable distances. And then the universe will be uniform. Not empty. There will still be photons, particles, quantum fields. But everything will be at the same temperature. Everything will be in equilibrium. This state has a name. Heat death. Not because everything dies in fire, but because heat itself dies. The differences die. The flows stop. At that point, there will be no warm and cool. No high energy and low energy. Just energy spread so evenly, so thinly, that nothing can happen anymore. Stars can't form. They need dense clouds of gas to collapse. But density requires difference. And there won't be any. Life can't exist. Life requires energy gradients, food that's higher in energy than waste, a sun that's hotter than the ground, temperature differences to drive chemical reactions. Without difference, there's no flow. Without flow, there's no change. Without change, there's no time in any meaningful sense. The universe will still exist, but nothing will happen in it. This is far away. So far away that the numbers stop making sense. 10 to the power of 100 years, maybe more, depending on what particles decay and how. A timeline so long that human civilization, all of recorded history, all of Earth's existence, is less than a blink. But it's still where things are going. Not because of some catastrophe. Not because of entropy accelerating or the universe breaking. Just because heat spreads. And the universe gives it infinite room to spread into. You can't stop this. There's no way to reverse it on a cosmic scale. You can't gather all the radiated light back to the stars. You can't compress the universe to make it denser again. The expansion continues. The cooling continues. The evening out continues. One day the universe will be the same temperature everywhere. Not hot. Not cold in the way we think of cold. Just uniform. A vast, dark, evenly distributed sea of low-energy radiation. No stars. No galaxies. No light. No motion that leads anywhere. Room temperature. If the room were infinite and empty, and had been cooling for eternity. But tonight, you're here. The universe is still young, still full of stars, still warm in places, still different. And you can feel that difference. The warmth of your blanket, the coolness of the air, the heat from your skin radiating into the room. Small reminders that the evening is long, but not over yet. A book slides across a table. Someone has pushed it. It moves quickly at first, covering distance in a smooth glide, its weight distributed evenly across the surface beneath it. Then it slows. No one touched it again. No hand reached out to stop it. The table didn't tilt. The air didn't suddenly thicken. But the book stops anyway, coming to rest a few feet from where it started. The motion is gone. Or rather, the motion has transformed into something else entirely, something you can't see by looking at the book or the table or the space between them. The energy that was propelling the book forward has been redistributed into heat, absorbed by the wood grain of the table and the fibres of the book's cover, and even the air molecules that were pushed aside as the book moved through them. Friction kept the books. Not friction as a force that destroys, but friction as a process that translates visible motion into invisible motion, taking the organized kinetic energy of the book and scattering it across billions of microscopic interactions. Each tiny point of contact between the book and the table experienced a collision. Each collision transferred energy. The table's surface is not smooth, not really. Under magnification, it's a landscape of peaks and valleys, wood fibres jutting upward in irregular patterns, and the book's cover has its own texture, its own microscopic roughness. As the book slid, these surfaces dragged against each other. The peaks on the book caught on the peaks on the table. They compressed slightly, bent, released, vibrated. That vibration is heat. The molecules in the wood and in the book cover were already vibrating before the slide began, jittering in place with thermal energy. But now they're vibrating slightly faster because the book's motion has been added to their existing motion. The book gave them energy, and in return, the book slowed down. This is the trade. Every time you slide something across a surface, every time you rub your hands together, every time you brake a car or drag a chair or scuff your foot on the ground, you're making this same exchange. Kinetic energy becomes thermal energy. Visible motion becomes invisible motion. And the universe tracks it. Not through intention or awareness, but through the simple fact that energy has to go somewhere, and when it leaves one form, it must enter another. The total amount never changes, but the distribution does. If you touch the table right where the book slid, you might feel a slight warmth. Probably not. The energy transferred is small, dispersed across a large area, mixed into the existing thermal energy of the wood. But it's there. Measurable if you had sensitive enough instruments. The book doesn't remember this transaction. It sits still now, indistinguishable from a book that was always still. The table doesn't remember either. The heat that entered its fibres has already started spreading outward, diffusing into the surrounding air, equalizing with the room. But the accounting is complete. The book's motion didn't vanish. It relocated. Friction doesn't steal energy. It just disperses it. This happens at every scale. A meteor enters the atmosphere, and friction with the air heats its surface until it glows, sometimes bright enough to see from the ground. And most of the meteor's kinetic energy is converted to heat and light before it ever reaches the surface. The energy doesn't disappear. It spreads into the atmosphere as warmth, as ionized particles, as sound waves that ripple outward and fade. A glacier moves down a mountain, and the ice at its base melts from the friction with the bedrock beneath it, creating a thin layer of water that actually helps the glacier slide more easily. But even that process is friction at work, turning the gravitational potential energy of the ice into heat, which melts the ice, which changes the system. The energy moves, always moves. You can feel this process most directly in your own hands. Rub them together quickly and they warm within seconds. The motion of your palms sliding against each other compresses and bends the skin, vibrates the cells, agitates the molecules. That agitation is heat. Your hands are warmer now than they were before you started rubbing them, and the energy that warmed them came from your muscles, which got it from the chemical bonds in the food you ate, which got it from sunlight that struck plants or fed animals. All of it traced back, step by step, through a chain of transformations. And all of it, eventually, ending as heat. Dispersed. Irretrievable. The book on the table participated in this same chain, though its path was shorter. Someone's hand pushed it. That hand's muscles contracted. The energy came from glucose, from ATP, from metabolic processes. And now that energy is in the table, in the book, in the air. Friction is often taught as something to overcome, an obstacle, a loss, a problem to be solved with lubricants and smoother surfaces. And in engineering, that's true. Reducing friction increases efficiency. But friction isn't a flaw in the universe. It's a consequence of surfaces interacting, of atoms and molecules bumping into each other in ways that transfer energy. Without friction, the book would slide forever, or until it hit something. Without friction, you couldn't walk because your feet wouldn't grip the ground. You couldn't hold a cup because it would slip through your fingers. Friction connects things, and in connecting them, it spreads their energy between them. The book has stopped. The table holds it. The motion that brought the book here is now part of the warmth of the room, distributed so finely across so many molecules that it can never be gathered back into motion. The slide is over. The energy remains. Accounted for. Scattered. Still. Somewhere else, another book is sliding across another table. Another trade is being made. Another small conversion. The universe keeps its books balanced. Always. And the book on the table rests. Unmoving. Warmer than it was by an amount too small to notice. But the ledger knows. A log burns in a fireplace. The flames are orange and yellow, moving upward, curling at the edges where they meet cooler air. The wood is breaking apart. Not just splitting or cracking, but coming undone at the molecular level. Cellulose and lignin, the long chain molecules that gave the wood its structure, are being torn apart by heat. The carbon and hydrogen atoms that were locked together for years are now separating, recombining with oxygen from the air. This is combustion. The log didn't always hold this energy. It accumulated it slowly over the years the tree was alive through photosynthesis. Sunlight struck the leaves. Chlorophyll absorbed specific wavelengths. Carbon dioxide from the air and water from the soil were pulled together, bonded into glucose, then into cellulose. The energy from sunlight was stored in those bonds, trapped there, waiting. And now the fire releases it. The flames don't create energy, they just unlock what was already there. The chemical bonds break, and the energy that held them together is freed. Some of it becomes light, photons radiating outward into the room. Some becomes heat, warming the air, the brick, the metal grate. Most becomes heat. The light you see is a side effect, a visible trace of electrons jumping between energy states as the carbon and oxygen atoms rearrange themselves. The photons escape at the speed of light, carrying energy away from the fire and into the room, or through the window, or up the chimney and into the night. They don't come back. The heat moves differently. It radiates from the flames as infrared, invisible but felt. It warms the air directly through contact. The hot gases rise, pushing cooler air aside, creating a current that pulls fresh oxygen into the base of the fire and carries smoke upward. The energy spreads in every direction. If the fireplace has glass doors, some of the infrared strikes the glass and warms it. The glass then radiates heat into the room and also conducts heat through its thickness to the air on the other side. If the fireplace is open, the heat flows more freely, but much of it escapes up the chimney, carried by the rising column of hot air. Either way, the energy disperses. The log burns for an hour, maybe 2. It depends on the wood's density, its moisture content, how much air reaches the flames. Oak burns slowly. Pine burns fast. But both release roughly the same amount of energy per kilogram of wood. And both end the same way. The flames consume the solid structure, leaving behind ash and charcoal, the remnants of carbon that didn't fully oxidize. The ash is light, fragile, mostly mineral content that couldn't burn. The charcoal is pure carbon, blackened and porous. But the energy that was stored in the wood? That's gone from the log entirely. It's in the room now. In the walls. In the air outside. Some of it warmed the people sitting nearby, absorbed by their skin, raising their body temperature slightly before being radiated away again. Some of it heated the bricks of the fireplace, which will continue radiating warmth for hours after the fire goes out, slowly cooling as they release what they absorbed. The light that escaped through the window travelled until it struck something, a tree, a house, the ground. Then it was absorbed, converted to a tiny increase in temperature at the point of impact. None of it can be gathered back. The energy that came from one log, bundled tightly in chemical bonds, is now distributed across an entire house, a yard, a neighbourhood. Spread so thin that it's imperceptible. The fire scattered it. This is what fire does. It takes concentrated energy and expands it outward in every form it can manage. Light, heat, sound, motion. The crackle of burning wood is energy moving through air as pressure waves. The glow is energy radiating as photons. All of it moving away from the source. If there were no chimney, if the room were perfectly sealed, the total energy in the room would increase by exactly the amount stored in the log. The air would grow warmer. The walls would heat up. Eventually the room would reach a new equilibrium, slightly hotter than before. But even then, the energy would be dispersed, not concentrated in one place, not available to burn anything else. The log took years to build its energy reserves. Seasons of sunlight, absorbed leaf by leaf, converted into sugar, transported through the tree's vascular system, deposited as cellulose in the trunk. The fire released it in minutes. That asymmetry is striking. Building takes time. Breaking releases quickly. The energy stored slowly becomes energy dispersed rapidly. And once dispersed, it's functionally gone. You could, in theory, gather all the heat from the room and concentrate it back into chemical bonds. You could use that energy to synthesize new molecules, rebuild cellulose, create another log. But the energy required to do that, to organize, to concentrate, to reverse the dispersal, would exceed the energy you'd recover, by far. So the process doesn't reverse. Not naturally. The log burns. The fire scatters what the tree gathered. The room grows warm. The energy thins. And somewhere, in a forest, another tree is still gathering sunlight, still building, still concentrating energy into bonds that will, one day, be broken. The cycle continues. But it's not a closed loop. Each turn through the cycle loses a little more to dispersal, a little more to the room, to the air, to the sky. The fire doesn't know this. It just burns. The log doesn't mourn. It just releases. And the energy, once bundled, once stored, once contained in a single object you could hold in your hands, spreads outward into a space too vast to measure. Irretrievable. Scattered. Like embers. Rising. Fading. Gone into the night. You're lying still right now. Your body rests against the mattress. Your breathing is slow. Your muscles have released their tension. But you're not still. Not really. Inside you, molecules are moving. Water molecules in your cells tumble and rotate, colliding with proteins and lipids thousands of times per second. Sodium and potassium ions drift through channels in cell membranes. ATP molecules release phosphate groups, transferring energy to molecular motors that crawl along cytoskeletal filaments. All of this is motion. Your body temperature is stable, around 37 degrees Celsius, and that stability exists only because of constant molecular activity. Heat generated by metabolism balances heat lost to the air. Your cells burn glucose continuously, breaking chemical bonds to extract energy, using that energy to maintain order inside themselves. The stillness you feel is macroscopic, a human-scale perception. But zoom inward and everything is vibrating. The atoms in your bones oscillate around fixed positions, held in place by electromagnetic forces, but never truly motionless. Even at body temperature, even in solid tissue, thermal energy keeps particles in motion. This is what temperature is. Not some separate quality imposed on matter, but the measure of how fast particles are moving on average. Hot objects have fast-moving molecules. Cold objects have slower ones. But nothing with temperature above absolute zero is completely still. The air around you is the same. It feels motionless, especially if the room is quiet and the windows are closed. But the nitrogen and oxygen molecules that make up that air are traveling at hundreds of meters per second in random directions. They collide with each other constantly. Each molecule moves in a straight line until it hits another molecule, then bounces off at a new angle, its speed changing slightly depending on the collision. Billions of collisions per second, per molecule. A chaotic ballet of invisible particles filling the space between you and the walls. You don't feel this motion because the collisions average out. The air pushes on your skin from all directions equally. The forces cancel. What remains is pressure, a steady force distributed across your body's surface, but the motion is still there. If you could see individual molecules, the air would look frantic. Particles zipping past each other, some moving faster, some slower, all of them trading energy through collisions. The temperature of the air is just the average kinetic energy of those particles. Average, not uniform. At any given moment, some molecules are moving much faster than average, and some much slower. The distribution is statistical. Most cluster near the average speed, but there's a tail extending in both directions, very fast molecules and very slow ones. This variation is why evaporation happens. A glass of water sits on a table. The surface looks calm, but at the boundary between liquid and air, water molecules are escaping. The fastest ones, the ones with enough kinetic energy to overcome the attraction of neighboring molecules, break free and become vapor. The liquid loses its fastest molecules. What remains is cooler. This is why evaporation cools things. Not because energy leaves the system entirely, but because the highest energy particles leave, lowering the average energy of what's left behind. Your skin does this when you sweat. Water on your skin absorbs heat from your body, warming the water molecules until the fastest ones evaporate. They carry energy away as vapor. Your skin cools. The energy didn't vanish. It's in the air now, distributed among the water vapor molecules. Even objects that look completely inert are full of motion. A metal spoon lying on a counter. Its atoms are locked in a crystalline lattice, but they vibrate around their equilibrium positions. The hotter the spoon, the more vigorous the vibration. Cool the spoon down and the vibrations slow. But they never stop completely unless you reach absolute zero, and absolute zero is unreachable. The third law of thermodynamics says you can approach it, but never arrive. As you cool something, removing energy bit by bit, each bit becomes harder to remove. The process asymptotically approaches 0 Kelvin. Scientists have cooled atoms to billionths of a degree above absolute zero, but never to zero itself. At those temperatures, quantum effects dominate. Atoms stop behaving like individual particles and start acting like waves. Their motion becomes governed by uncertainty principles. They can't be perfectly still, because being perfectly still would mean having a perfectly defined position and zero momentum simultaneously, which quantum mechanics forbids. Even at the coldest temperatures ever achieved, motion persists. This means the universe has no true stillness, no place where energy stops moving entirely. Even the vacuum of space isn't empty. Quantum fields fluctuate, creating and annihilating virtual particles constantly. Motion is fundamental. You feel still because your consciousness operates at a scale far above molecular motion. You perceive your body as a single coherent object, not as a collection of trillions of vibrating particles. But the particles don't care about that perception. They move regardless. The bed beneath you is vibrating. The pillow. The air. Your skin. The blood in your veins. The neurons firing in your brain as you process these words. All of it is motion. All of it is energy distributed across countless particles, each one moving in its own direction, each one contributing to the whole. Stillness is just what we call it when the motions are too small to see, when they average out, when the chaos balances itself. But the energy is there, always. And it will remain there, in some form, long after you've gotten up and left the room. The warmth you gave to the mattress, the breath you exhaled into the air, the heat that radiated from your skin, all of it still moving, still vibrating, still there, just invisible, just scattered, just what we mistake for stillness. A refrigerator hums in a kitchen somewhere, its compressor running steadily, and inside the freezer compartment, water is becoming ice, while the room outside grows imperceptibly warmer. This is not a simple trade. To freeze water, you must remove heat from it, extracting thermal energy molecule by molecule, until the water molecules slow down enough to lock into a crystalline structure. But that heat doesn't disappear, and it doesn't simply drift away on its own, because heat will not flow from cold to hot without help. The refrigerator provides that help by doing work, by running an electric motor that drives a compressor that forces refrigerant through a cycle of compression and expansion, and in the process, the heat removed from inside the freezer is deposited outside, into the coils on the back of the appliance, where it radiates into the kitchen air. The kitchen warms more than the freezer cools. This is unavoidable, not a flaw in the design, but a consequence of how energy behaves when you force it to move against its natural direction. The refrigerator consumes electrical energy to pump heat from a cold place to a warm place, and some of that electrical energy is converted to additional heat in the process. Heat generated by friction in the motor, resistance in the wiring, inefficiencies in the compressor. All of that extra heat also ends up in the kitchen. So the total heat in the room increases, even as the freezer gets colder. The ice forms slowly, water molecules losing kinetic energy as the temperature drops, their random tumbling motion becoming more restricted until they settle into fixed positions in a hexagonal lattice. The structure is open, with space between the molecules, which is why ice is less dense than liquid water and why it floats. The molecules are still vibrating in place, still moving, but they're no longer free to slide past each other. This transition from liquid to solid releases energy, a small amount called latent heat, because the molecules in the liquid state had more potential energy stored in the freedom to move, and when they lock into a lattice, that potential energy is released as heat. The refrigerator has to remove that heat too, on top of the heat required to lower the water's temperature from room temperature to freezing. the work piles up. The refrigerant inside the system undergoes its own transformations, absorbing heat inside the freezer when it evaporates from liquid to gas, then releasing that heat outside when it's compressed back into a liquid. The cycle repeats continuously as long as the compressor runs, moving heat from inside to outside, maintaining the temperature difference between the freezer and the room. But maintaining that difference requires constant energy input. If you turned off the refrigerator, the freezer would begin warming immediately, heat flowing in from the warmer kitchen through the insulation, through the door seals, through any gaps or imperfections in the thermal barrier. The ice would melt. The system would equilibrate. The temperature difference would vanish without the compressor's work to sustain it. This reveals something fundamental about order and disorder, about concentrated states and dispersed states, because the frozen water represents a more ordered configuration than liquid water, molecules locked in place rather than tumbling freely, and creating that order locally requires creating more disorder elsewhere. The heat dumped into the kitchen represents increased molecular motion in the air, increased randomness, increased entropy. The total disorder increases even as the freezer becomes more ordered. You could calculate the exact amounts if you knew the efficiency of the refrigerator, the volume of water being frozen, the temperature of the kitchen, but the principle holds regardless of the numbers. Every joule of heat removed from the freezer requires more than 1 joule of energy input, and the difference is dissipated as waste heat. The universe does not allow free organization. This is true not just for refrigerators, but for any process that creates order, whether it's a living cell assembling proteins, a factory manufacturing products, or a person cleaning a room. Order in one place demands greater disorder somewhere else, usually in the form of heat released during the process. The cell generates waste heat as it metabolizes nutrients. The factory's machines heat up as they run. The person cleaning expends energy from food that was produced by plants that scattered most of the sunlight they absorbed as heat. The refrigerator is simply a clear example, a machine whose entire purpose is to create a local temperature difference by moving heat against its preferred direction, and the cost of doing so is written into the rising temperature of the kitchen and the electricity meter outside. If the kitchen were perfectly insulated from the rest of the house, if it were a closed system with no energy entering or leaving except through the electrical outlet powering the refrigerator, then the kitchen would warm faster than the freezer cools. The net effect would be an increase in the room's total thermal energy. The ice would form, yes, but the air around the refrigerator would grow noticeably warmer. Order here, disorder there, and more disorder overall. This asymmetry appears everywhere once you start looking for it. Air conditioners cool buildings by heating the outside air. Heat pumps warm houses by cooling the ground or the outside air. Every such device moves heat from where you don't want it to where you do, and every such device consumes energy to do so, and every such device increases the total entropy of the universe even as it decreases entropy locally. Nothing escapes this pattern. The ice in the freezer will remain frozen as long as the refrigerator keeps running, as long as energy flows in from the electrical grid to power the compressor. But if that flow stops, the ice will eventually melt, and the freezer will warm, and the difference will collapse back into sameness. The order is temporary. The disorder is permanent. The kitchen hums. The ice forms. The heat disperses. And somewhere, a power plant burns fuel, or splits atoms, or captures sunlight, converting concentrated energy into electricity that flows through wires to the refrigerator, which uses it to move heat uphill, which generates more heat in the process, which radiates into the world and joins the vast background warmth of everything slowly evening out. The cost of making ice is heat. Always more heat than cold. Always more disorder than order. The refrigerator doesn't apologize for this. It just runs. Humming. Working. Paying the price the universe demands. A puddle forms after rain. Water collects in a shallow depression in the pavement, reflecting sky and clouds. By morning, it's gone. No one drained it. No hand reached down to wipe it away. The water simply left, molecule by molecule, rising into air that was waiting to receive it. This is evaporation. At the surface of the puddle, water molecules are moving. They vibrate. They rotate. They collide with neighbours beneath them and air molecules above them. Most stay in the liquid, but some escape. The ones that escape are the fastest. They have enough kinetic energy to break the hydrogen bonds holding them to other water molecules. They push through the surface and become vapour. They don't come back. Once a molecule enters the air, it moves freely, bouncing between nitrogen and oxygen molecules, travelling in random directions until it collides with something else. It might eventually condense back into liquid somewhere, on a cold window or in a cloud, but it won't return to the puddle. That puddle is shrinking. And as it shrinks, it cools. This is the part that matters. The puddle loses its fastest molecules. What remains has lower average energy. Lower energy means lower temperature. You can feel this yourself. Step out of a shower. Water clings to your skin. As it evaporates, your skin feels cool. Not because the water was cold, but because evaporation carries heat away. The energy doesn't vanish. It transfers to the water vapour. The molecules that escaped now carry the kinetic energy they had as liquid, but they're in the air now, contributing to the thermal motion of the atmosphere. The puddle has no choice in this. It can't hold back its fastest molecules. They leave when they have enough energy. The liquid just sits there, shrinking, cooling, offering up its surface to the air. Selection happens at the boundary. Not all molecules have the same speed at any given moment. Temperature is an average, a statistical measure. Some molecules move faster than that average. Some move slower. The distribution is broad. The fastest ones escape first. They're the outliers. They have 2 or 3 times the average energy, and that's enough to overcome the attraction of the liquid. The slower ones stay. This means evaporation is self-limiting in a closed container. If you seal water in a jar, molecules still evaporate from the surface, but they can't escape the jar. They bounce around in the air above the water. Some collide with the surface and stick. Eventually, the rate of evaporation equals the rate of condensation. That's equilibrium. The air in the jar is saturated. It can't hold more vapour at that temperature. But in an open puddle, there's no equilibrium. The vapour escapes into the wider atmosphere. Wind carries it away. Diffusion spreads it. The puddle keeps losing molecules and never recovers them. It evaporates completely. Humidity affects this process. Air that's already holding a lot of water vapour gives evaporating molecules less room to escape into. The rate slows. On a humid day, puddles linger. On a dry day, they vanish quickly. Temperature affects it too. Warmer water has more high-energy molecules, more candidates for escape. A hot puddle evaporates faster than a cold one. But even cold water evaporates eventually. Even ice. Sublimation. Molecules leave the solid surface directly and become vapour without melting first. The process is slower, but it happens. Your breath contains water vapour. It came from your lungs, where moisture evaporated from the lining of your airways. That water came from what you drank, from fluids in your bloodstream. And those fluids came from food, from rivers, from rain, from oceans. All of it cycling through evaporation and condensation. Water leaving surfaces. Water forming clouds. Water falling again, but never returning to the same puddle. The energy flows with the water. When vapour condenses into rain, it releases the latent heat it absorbed during evaporation. That heat warms the air. Storms are powered by this process. Evaporation from warm ocean surfaces loads the atmosphere with vapor. The vapor rises, it condenses, it releases heat. That heat drives wind. The puddle doesn't know it's participating in this. It just evaporates, and what it leaves behind is a dry patch of pavement, slightly cooler than it would have been, marked only by a faint ring of dust or minerals that were dissolved in the water. The water is gone. The energy went with it, distributed into the air as molecular motion, carried away by wind, mixed into weather patterns. Irretrievable. Another puddle will form after the next rain, but it won't be the same water. It won't be the same molecules. It will just be another temporary collection, another surface offering itself to the air, waiting to lose its fastest, waiting to cool, waiting to vanish. Evaporation peels energy away in layers. The fastest leave, then the next fastest, then the next. What remains grows cooler, slower, smaller, until nothing is left. Just pavement, just absence, just the memory of water. Written in dryness. A bell rings. Someone struck it with a mallet. Metal vibrates. The air around it begins to move. For a moment the sound is sharp and clear. Then it fades. Not all at once, but gradually, the tone diminishing until only silence remains. The energy didn't disappear. When the mallet hit the bell, it transferred kinetic energy to the metal. The impact compressed the surface slightly, creating a distortion that travelled through the material as a wave. The bell's structure flexed and returned, oscillating at its natural frequency. That oscillation pushed air. The vibrating metal surface acted like a piston, compressing the air molecules immediately adjacent to it, then pulling back and creating a region of lower pressure. Those pressure differences propagated outward as sound waves, alternating compressions and rarefactions moving through the air at roughly 343 meters per second. The sound spread in all directions. At first, close to the bell, the wave was strong. The pressure variations were large enough to vibrate your eardrum noticeably if you stood nearby. But as the wave travelled, it expanded into an ever larger sphere of air. The same amount of energy was now distributed across a growing volume. The intensity decreased with distance, not because energy was lost, but because it was shared among more and more air molecules. The sound wave didn't travel alone. As it moved, it encountered air molecules that were already in motion, already vibrating with thermal energy. The wave's organized motion, molecules moving together in the same direction, mixed with the random motion of ordinary air. Order became disorder. Each air molecule that was pushed by the sound wave collided with other molecules. Some of those collisions transferred energy in the direction of the wave, allowing it to propagate. But some transferred energy in random directions, converting the wave's organized motion into thermal motion. Heat. This process is called absorption, though nothing is truly absorbed in the sense of disappearing. The sound energy transforms into the kinetic energy of individual molecules moving in random directions. The air warms by an infinitesimal amount. If the bell rang in a closed room, the sound waves would also strike the walls, the floor, the ceiling. Some of the wave's energy would reflect back into the room. Some would cause the walls themselves to vibrate slightly, and those vibrations would dissipate as heat within the material. Bit by bit, the organized motion scattered. The bell itself lost energy as it vibrated. The metal's internal structure isn't perfectly elastic. As it flexed, microscopic friction within the crystal lattice converted some vibrational energy into heat. The bell warmed by an amount too small to measure easily, but it warmed nonetheless. Within seconds, the sound was gone from perception. Your ears could no longer detect it. The air pressure variations had become too small to register. But the energy was still present, distributed among trillions of air molecules, now moving slightly faster than they were before the bell rang. You could not reverse this process. You could not gather the scattered molecular motion back into organized sound waves. You could not make the air molecules move in unison again, compressing and expanding in a coordinated pattern that would reconverge on the bell. The information is lost. The sound wave carried structure, frequency, amplitude, harmonics, the specific shape of the pressure variation that made the bell sound like a bell and not like something else. That structure dissolved into randomness. The thermal motion of air has no memory of the bell's tone. It just vibrates. This is true of all sound. A voice, a song, thunder, an explosion. All of them convert organized motion into disorganized motion. A voice travels through air, carrying vibrations shaped by vocal cords and resonant cavities in the throat and mouth. Those vibrations encode information, phonemes, pitch, inflection. But as the sound spreads and weakens, that information becomes unrecoverable. The energy persists. The meaning fades. In space, where there is no air, sound cannot propagate. Strike a bell on the moon and it vibrates silently. The energy remains in the bell, dissipating as heat through internal friction. There are no molecules to push, no medium to carry the wave. This makes sound fundamentally different from light. Light doesn't need a medium. Photons travel through vacuum without scattering into thermal motion. They can cross billions of light years of empty space and still carry information about their source. Sound cannot do this. Even in air, sound is fragile. It disperses quickly. A shout travels maybe a kilometre before it's indistinguishable from background noise. A whisper barely crosses a room. The energy spreads not just through space, but through time. The wave passes a given point in the air. The molecules there vibrate for a fraction of a second, and then the wave is gone. Those molecules continue moving, but now randomly, no longer carrying the structure of the sound. The wave has moved on. Or more accurately, it has transformed. Some sounds are preserved indirectly. Recordings capture the pressure variations and store them as magnetic patterns or digital data. Playback recreates the sound by vibrating a speaker in the same pattern. But that's not the original sound. That's a copy. The original energy, the specific molecules that were set in motion when the bell first rang, scattered into thermal noise moments after the sound began. Unrecoverable. The bell sits silent now, cooler than it was immediately after being struck, having radiated the vibrational energy into the surrounding air. The air is warmer by an amount no thermometer would detect. The sound is gone. Not destroyed, just dispersed, just transformed into motion too chaotic to reassemble. Somewhere else, another bell will ring. Another wave will spread. Another structure will dissolve. And the air will accept it, as it always does. Without record, without memory, just warmth, just motion, just the faint echo of what was once a clear tone, now scattered, now thermal, now silent. Time feels like it moves in one direction. Forward. Always forward. You remember yesterday, but not tomorrow. You age, but never grow younger. Events happen in sequence, and that sequence doesn't reverse. But why? The laws of physics, at their most fundamental level, don't distinguish between forward and backward in time. Newton's equations work the same way if you replace time with negative time. The same is true for quantum mechanics, for electromagnetism, for general relativity. The mathematics doesn't care which direction time flows. Yet you've never seen a shattered cup reassemble itself. You've never watched smoke flow back into a candle. You've never seen heat spontaneously concentrate from cool surroundings into a hot object. These things don't happen. Not because the laws forbid them, but because the initial conditions required are so improbable they might as well be impossible. And that improbability is what we call time. Drop a cup and it falls. Gravity pulls it downward. It accelerates. It strikes the floor and shatters. Kinetic energy transforms into sound, into deformation of ceramic, into heat. The pieces scatter. Energy disperses. You could, in theory, reverse every particle's velocity at the moment of impact. Every fragment moving outward could be sent back inward with exactly the same speed. Every vibration in the floor could reverse direction. Every air molecule disturbed by the sound wave could retrace its path. If you could coordinate all of this perfectly, the cup would reassemble. The physics allows it. But you can't coordinate it. There are too many particles, too many degrees of freedom. The information about each particle's exact position and velocity at the moment of shattering spreads into the environment immediately. It becomes encoded in the thermal vibrations of the floor, in the motion of air molecules, in the deformation of surfaces the fragments touched. That information doesn't disappear, but it becomes practically irretrievable. This is the difference between microscopic reversibility and macroscopic irreversibility. Individual particle interactions are reversible. A collision between two molecules looks the same forward or backward in time. But when you have billions of particles interacting, the collective behavior becomes directional. Order becomes disorder. Concentrated energy disperses. And that direction is time's arrow. Entropy increases. Not because of a law that forces it, but because there are vastly more disordered states than ordered ones. A shattered cup can arrange its pieces in countless ways. An intact cup has only one arrangement. Random changes favor the countless over the one. Statistical probability creates the flow of time. Ice melts in warm water. The organized structure of the ice lattice breaks down. Water molecules that were locked in place now move freely. The cold and hot regions mix. Eventually, everything reaches the same temperature. You never see the reverse. A glass of lukewarm water spontaneously separating into ice and hot water. Not because the energy wouldn't be conserved, it would. Not because physics forbids it, it doesn't. But because the odds of all those molecules spontaneously organizing themselves that way are so astronomically small that it would never happen even if you waited longer than the universe has existed. The mixing is irreversible in practice, even if not in principle. This is why you can scramble an egg but not unscramble it. Why you can burn wood but not unburn it. Why you can age but not reverse aging. Each process takes an organized state and transforms it into a less organized one. Each process increases the total number of possible arrangements the system could be in. And once the arrangements proliferate, going back requires coordination that nature doesn't provide. Your memories are recordings of lower entropy states. The past is remembered because it was more ordered than the present. Your brain stores information about configurations that no longer exist. But you can't remember the future because the future hasn't been configured yet. It's still probabilistic, still a vast space of possible arrangements that haven't collapsed into actuality. Time moves forward because disorder increases, and disorder increases because there are more ways to be disordered than ordered. The universe began in a highly ordered state. The Big Bang was a moment of extreme concentration, extreme organization. All the energy that would ever exist packed into an incomprehensibly small volume. And ever since, it's been spreading, expanding, dispersing. Galaxies formed from that dispersion. Stars ignited. Planets coalesced. Life emerged. All of it riding on the gradual slide from order to disorder, extracting usable energy from the difference between the hot and the cold, the dense and the diffuse. We exist in the middle of that slide. If the universe had started in a state of maximum disorder, nothing would happen. No events. No change. Just equilibrium stretching eternally. Time wouldn't flow because there would be no difference between one moment and the next. But it didn't start that way. It started ordered, and it's unwinding. Every process you observe is part of that unwinding. Every cup that shatters, every sound that fades, every heat flow from warm to cool, every breath you exhale, every star that burns and cools. All of it moving in the same direction. Not because time forces them to, but because that's the direction disorder points. Time is what we call the shape of entropy increasing. A river flows downhill, not because downhill is forward in time, but because gravity pulls water toward lower elevation, and we assign the direction of flow to time's arrow. Energy disperses. We call that direction later, and so clocks tick forward. Not because forward is special, but because backward would require gathering what has scattered, organizing what has mixed, reversing what has spread. And the universe doesn't keep the map for that. It doesn't forbid it. It just makes it so unlikely that in all the time that has passed and all the time that will pass, it might never happen once. The cup stays broken. The smoke stays dispersed. The energy stays scattered. And time, without effort, without force, without law, points in the only direction it ever could. Forward. Always forward. Drop a stone into the ocean. Your hand releases it. Gravity pulls it downward through air, then through the surface tension of water. It enters with a splash, displacing liquid, creating a cavity that collapses behind it. The stone sinks. The water remembers, briefly. The impact generates waves that ripple outward in concentric circles, carrying energy away from the point of entry. Each wave is a disturbance in the surface, a rise and fall that propagates through the coupling of water molecules, each one pulling on its neighbours through hydrogen bonds and gravity. The circles expand. At first, close to where the stone entered, the waves are distinct. You can see them clearly, track their motion, count the peaks and troughs. The energy from the stone's fall is concentrated in a small area, and the waves are tall enough to be obvious. But they spread. As the circles grow wider, the same amount of energy distributes across a larger circumference. The wave height decreases. The disturbance thins. What was a noticeable peak becomes a gentle undulation, then a ripple barely visible against the ocean's natural texture. The energy doesn't vanish. It just dilutes. The waves also transfer energy to the water itself as they move. Some energy goes into lifting water molecules against gravity as each peak forms. Some goes into friction between layers of water moving at different speeds. Some radiates downward as pressure waves that fade into the depths. The organized motion becomes disorganized motion. The wave becomes warmth. Within seconds, the surface where the stone entered looks much like the surface everywhere else. Small waves from wind, currents, the random chop of an ocean that never stops moving. The stone-generated wave has merged with the background. If you were floating on the water 100 meters away, you might feel the wave pass beneath you. A gentle rise and fall, barely perceptible. You wouldn't know what caused it. You wouldn't know a stone was thrown. The ocean doesn't label its disturbances. The stone itself has settled on the ocean floor by now, or is still sinking through deep water, depending on where you threw it. Its potential energy, the height it had above the water surface, converted first to kinetic energy during the fall, then to the energy of the splash, then to the spreading waves, then to heat dispersed through countless collisions. The stone is gone from the surface. The energy remains scattered. You could not reconstruct the original event by observing the ocean 5 minutes later. The information has been erased by mixing. The wave's shape, direction, amplitude, frequency, all of it dissolved into the ocean's ongoing turbulence. This is how large systems forget. The ocean is vast. It contains roughly 1.4 billion cubic kilometers of water. Each cubic meter holds trillions upon trillions of molecules. When you add energy to it, through a stone, through wind, through heat from the sun, that energy spreads through an incomprehensibly large number of particles. And once spread, it's anonymous. The ocean doesn't remember yesterday's waves. It doesn't hold a record of where each current came from. It just moves. Molecules circulate through convection, driven by temperature differences, by the rotation of the Earth, by the pull of the moon. But there's no archive, no memory stored in the water itself. If you threw 1,000 stones in different locations, each would generate its own set of waves, and all those waves would overlap, interfere, combine. Crests would meet and amplify. Crests would meet troughs and cancel. The resulting pattern would be complex, chaotic, unreadable. And that pattern would fade just as the single wave faded. Into heat. Into the ocean's average motion. Into nothing you could trace back to its source. This forgetting happens at every scale. A raindrop strikes the surface. Forgotten in seconds. A ship passes, churning wake behind it. Forgotten in minutes. A hurricane stirs the ocean for days, mixing surface water with deeper layers, generating massive swells. Forgotten in weeks. The energy from the hurricane remains. It's in the circulation patterns, in the slightly elevated average temperature of the mixed water, in the new positions of countless particles that were moved and will never return to where they started. But the storm itself is gone. You are like the stone in some ways. You disturb the systems you move through. You displace air when you walk. You warm rooms with your body heat. You leave traces, thermal, kinetic, chemical. But the world forgets those traces quickly. The air you warmed mixes with cooler air. The surfaces you touched cool down. The space you occupied fills again with molecules that don't remember you were there. Not cruelty, not indifference, just scale. The environment is so much larger than any single disturbance that the disturbance becomes invisible almost immediately. The ocean has no reason to remember one stone. The atmosphere has no reason to remember one breath. They're too vast. The individual event is too small. This is different from a recording, which preserves information by encoding it in a stable medium. A photograph, a written word, a file on a hard drive. These things resist mixing, resist entropy locally, by maintaining organized structure. But the ocean is not a recording medium. It's a dynamic fluid. It moves constantly. It mixes constantly. And so it forgets. The stone is gone. The wave is gone. The splash, the sound, the brief upward fountain of water, all of it dissolved back into the ocean's ongoing presence. The ocean remains, unchanged in any way you could measure, just as deep, just as vast, just as indifferent to subtraction. You could throw another stone. The ocean would accept it the same way, with a splash, with waves, with spreading, and then with forgetting. Gentle, complete, as if nothing ever disturbed it at all. There's a question that appears simple at first, but opens into something vast when you sit with it long enough. A question about where things go when they seem to vanish. About what happens to the motion and heat and light that fill the world one moment and seem absent the next. Energy doesn't die. It can't. This is one of the most tested, most verified principles in all of physics: conservation of energy, the first law of thermodynamics, the recognition that the total amount of energy in a closed system never changes. It transforms from one form to another constantly, kinetic to thermal, chemical to radiant, potential to kinetic, but it never disappears and it never appears from nothing. And yet things fade. Sounds diminish. Fires burn out. Motion stops. So where does the energy go when these things happen? When a ringing bell falls silent, or a spinning top comes to rest, or the last ember of a campfire goes dark? It spreads. It diffuses into the environment so thoroughly, so completely, that it becomes indistinguishable from the background energy that was already there. Picture a single drop of ink falling into a swimming pool. At first, the ink is concentrated, visible as a dark streak or cloud in the clear water. You can point to it. You can say, "There it is." But the ink doesn't stay concentrated, because the water molecules around it are in constant thermal motion, jostling the ink molecules, carrying them in random directions. The ink spreads. It diffuses outward from where it started, moving into regions of the pool that were previously clear, and as it spreads, it thins. Eventually, the entire pool has a faint tint, so faint you might not even notice it unless you compared it to completely clear water, and at that point, you can no longer point to where the ink is because it's everywhere equally. The ink didn't vanish. Every molecule that entered the pool is still there, but it's distributed so evenly across such a large volume that it's no longer concentrated enough to be visible or meaningful in the way it was when you could see it as a distinct cloud. Energy behaves the same way in the universe, not because energy is a substance like ink, but because energy exists as motion, vibration, position, and those properties disperse when left alone. A car drives down a highway and then brakes to a stop. The kinetic energy of the moving car, the energy associated with its mass traveling at a certain velocity, doesn't vanish when the car stops. It transforms into heat in the brake pads and rotors as friction converts the organized motion of the car into the disorganized motion of molecules vibrating faster within the brake materials. The brake pads grow hot. That heat radiates into the surrounding air, warming it slightly. The air molecules that absorb the heat move faster, colliding with other air molecules, spreading the energy further. Within minutes, the brake pads cool back to ambient temperature, and the energy that was once the car's forward motion is now distributed among billions of air molecules across a stretch of highway, mixed into the thermal background so completely that you could never gather it back. The car could be driven again, could be accelerated to the same speed, but that would require new energy input from burning fuel, from the chemical bonds in gasoline releasing energy through combustion. The original kinetic energy, the specific energy the car had before it braked, is gone in the only way energy can be gone, not destroyed, but dispersed beyond recovery. This dispersal happens with every energy transfer. A light bulb glows, converting electrical energy into light and heat. The light photons travel outward in all directions at the speed of light until they strike a surface, a wall, the floor, your skin, and are absorbed, their energy becoming a slight increase in the temperature of whatever they struck. The heat generated by the bulb's inefficiency radiates into the room, warming the air, which rises and mixes with cooler air through convection. Turn off the light, and within hours the room returns to its previous temperature as the added heat escapes through windows, walls, ventilation, radiating or conducting into the larger environment outside. The energy that came from the electrical grid, that flowed through the filament or LED, that briefly illuminated the room, is now part of the outdoor air's thermal energy, mixed with energy from the sun, from car engines, from every other source of heat in the area. It's still there, still conserved, but no longer light, no longer concentrated, no longer useful in any practical sense. This is what the universe does with energy over time. It takes concentrated, organized, useful forms and spreads them into dilute, disorganized, diffuse forms that can't drive processes or do work or create change. And this spreading is why the universe has a direction, why time flows forward, why you can scramble an egg but not unscramble it. Because gathering what has spread requires knowledge of where every piece went and the ability to coordinate the reversal of trillions of individual particle motions simultaneously, which is possible in principle, allowed by the fundamental laws, but so improbable in practice that it might as well be forbidden. The universe contains a finite amount of energy, introduced at the Big Bang, or perhaps existing eternally in some models, but regardless of the total quantity, that energy is constantly redistributing itself from concentrated pockets into ever more diffuse configurations. Stars concentrate energy through gravitational collapse and fusion, creating regions of intense heat and light surrounded by the cold vacuum of space. But even stars are temporary concentrations. They radiate energy outward constantly, pouring photons into space. And those photons spread across increasingly large volumes as space itself expands. Eventually, every star will exhaust its fuel. Every concentration will dissipate. Every difference will level out. Not soon. Not in any time frame that matters to human concerns. But inevitably, given enough time, the universe trends toward a state of maximum diffusion, where energy is spread so evenly across all of space that no region is hotter or denser or more energetic than any other. At that point, nothing can happen, because happening requires difference. A hot region and a cold region, a dense region and a sparse region, a concentration of energy that can flow toward a deficit. Without difference, there is no flow. Without flow, there is no change. Without change, there is no time in any meaningful sense. Just an eternal equilibrium, where the universe exists but nothing within it evolves or transforms or moves toward anything new. That end state is far away, unimaginably far. But every process you observe is a small step in that direction. Every time energy spreads from where it's concentrated to where it's diffuse, every time heat flows from hot to cold, every time organized motion becomes random thermal vibration, the universe becomes slightly more uniform, slightly closer to equilibrium. You are part of this process. Your body maintains a temperature higher than your surroundings by constantly burning fuel, breaking chemical bonds in the food you eat, extracting energy, and releasing waste heat into the environment. You are a temporary concentration of energy, a pattern that persists only because you continuously import new energy and export entropy. When you stop eating, when metabolism ceases, your body temperature begins to match the environment. The difference erodes. The concentration disperses. This is not morbid. It's just how energy behaves. Every living thing, every star, every engine, every fire, maintains its concentrated state only by importing energy from elsewhere and exporting disorder. The moment that import stops, diffusion takes over. A cup of coffee sits on a table and cools. The heat energy in the coffee is concentrated relative to the room, so that energy flows outward through the ceramic, into the air, radiating as infrared, conducting through the table surface. The coffee cools. The room warms infinitesimally. The total energy remains constant, but its distribution changes, becoming more even. And once the coffee reaches room temperature, nothing else happens. The energy is still there, still in the room, but it's no longer concentrated enough in the coffee to make the coffee noticeably warm. You could reheat the coffee by adding new energy from a microwave or a stove, but that energy comes from elsewhere, electricity from the grid, which came from a power plant burning fuel or harnessing falling water or capturing sunlight. The original heat that left the coffee hours ago is gone, diffused into the room, mixed with the air, radiated through the windows into the outside world. Irretrievable. Not destroyed. Just spread too thin to gather. This is the answer to the question. Energy doesn't die when things fade or stop or cool. It diffuses into the vast environment surrounding the event, spreading across space, distributing among particles, thinning until it becomes part of the background rather than a distinct, traceable quantity. The universe is that environment, the ultimate surroundings. And every event, every process, every transformation adds a little more energy to the background, makes the universe slightly more uniform, slightly closer to the state where everything is the same temperature, the same density, the same energy per volume. A state where nothing can happen anymore, because happening requires difference, and difference is what diffusion erases. But tonight, there is still difference, still concentration, still flow. The universe is young enough, structured enough, that energy still clusters in stars and planets and living things, still moves from hot to cold, still drives the processes you experience as life and light and warmth. The diffusion is slow. Slow enough that countless generations will live and die before the differences diminish noticeably on cosmic scales. But the direction is set. The path is clear. Energy spreads. Always. Inevitably. And the universe, patient and vast, receives it all. Consider what happens when you clap your hands together. The motion is deliberate, controlled by muscles that contract in coordinated patterns, pulling your palms toward each other until they collide. The collision creates sound. But the sound doesn't come from nothing. It comes from the kinetic energy of your moving hands, energy that was in your muscles as chemical potential energy stored in ATP molecules, energy that came from the food you digested, which got its energy from sunlight captured by plants through photosynthesis. A chain of transformations leading to this single moment of impact. When your palms meet, they compress the air between them suddenly, creating a pressure wave that propagates outward in all directions. That's the clap sound, organized motion of air molecules moving together in a coordinated pattern. But the sound fades within seconds. The pressure wave spreads across the room, its intensity decreasing as it expands into a larger volume of air. Some of the wave's energy reflects off walls and furniture. Some is absorbed by soft materials like curtains or cushions, causing those materials to vibrate slightly and convert the organized wave motion into random thermal motion within their fibers. The air molecules that carried the sound continue moving after the wave passes, but now their motion is random rather than coordinated. They collide with other molecules, spreading the energy further, converting the last traces of organized sound into heat. Within a few seconds, the sound is inaudible. Within a minute, the energy is fully thermalized, distributed among air molecules throughout the room as a tiny, unmeasurable increase in temperature. The clap happened. The energy was real, but now it's gone from your perception, absorbed into the background thermal noise of the environment. This absorption, this conversion of organized energy into disorganized heat, is the universe's default behavior. Every sound that fades, every light that dims, every motion that stops, follows the same pattern. Concentration gives way to dispersal. A kettle boils on a stove. Heat from the burner transfers to the metal bottom of the kettle through conduction, then to the water through convection, as hot water rises and cooler water sinks, creating a circulation pattern. The water absorbs energy until it reaches 100 degrees Celsius at atmospheric pressure, at which point the energy goes into breaking the hydrogen bonds between water molecules, allowing them to escape the liquid as steam. Turn off the stove, and the boiling stops immediately. The water begins cooling. Steam condenses on nearby surfaces. The kettle radiates heat into the air. The metal cools. the water cools. All the energy that went into heating and boiling the water now leaves the system, dispersing into the kitchen. Some warms the air directly through convection. Some radiates as infrared through the air and is absorbed by walls, cabinets, your skin if you're standing nearby. The steam that escaped carries energy with it until it condenses somewhere, on a window, on a wall, on a cool pot lid, releasing its latent heat at the point of condensation. Within an hour, the kettle and water return to room temperature. The energy that concentrated in the kettle during boiling has spread throughout the kitchen, mixed into the thermal background. If the kitchen were perfectly insulated from the rest of the house, you could measure a slight increase in the average temperature of the room. But in a real kitchen, with doors and windows and ventilation, that energy escapes into adjacent rooms, into the outside air, dispersing across an even larger volume. Gone from the kettle. Gone from the kitchen. But not gone from existence, just spread so thin across so much space that reassembling it, gathering it back into the concentrated form it had when the water was boiling, would require more energy than you'd recover. This is the practical meaning of energy loss. Not literal disappearance, but dispersal to the point of uselessness. Engineers talk about waste heat, about inefficiency, about energy that's lost to the environment. What they mean is energy that's being converted to low-grade thermal energy and dispersed. A car engine converts chemical energy in gasoline into mechanical energy that turns the wheels. But most of the energy, roughly 70%, becomes heat that's expelled through the exhaust system and the radiator. That heat warms the air. It disperses. It's counted as loss because it doesn't contribute to moving the car, but the energy still exists. It's in the atmosphere now, mixed with heat from billions of other engines, from factories, from sunlight, from geothermal vents, from every process on Earth that releases heat. The atmosphere is a vast reservoir of thermal energy, constantly circulating, constantly mixing, constantly exchanging heat with the ground and the oceans and space. When you feel wind, you're feeling the atmosphere redistributing energy. Hot air rises in one region, cool air sinks in another, creating pressure differences that drive air movement. Thunderstorms are powered by the energy released when water vapor condenses into rain. That energy came from the sun evaporating ocean water days or weeks earlier. The sun's energy was stored temporarily in the water vapor, then released when the vapor condensed, driving the updrafts and downdrafts of the storm. And when the storm ends, that energy disperses too, into the broader circulation of the atmosphere, into rain warming slightly as it falls, into sound that fades into silence. The ocean is another vast reservoir, holding enormous amounts of thermal energy absorbed from sunlight over centuries. Ocean currents redistribute that energy across the globe, warming some regions, cooling others. But even the ocean's heat is slowly diffusing. Water at the surface radiates heat into space at night. Evaporation carries energy away as water vapor. Deep ocean water mixes with surface water over long timescales, distributing heat vertically. The ocean is warmer than space, so it's constantly losing energy to its surroundings, just like the cup of coffee on the table. The loss is slow because the ocean is enormous and well insulated by the atmosphere, but the direction is clear, toward equilibrium, toward diffusion. Even the Earth as a whole is diffusing energy. The planet receives energy from the sun during the day and radiates energy back to space at night. On average, the energy in equals the energy out, maintaining a roughly stable temperature. But the Earth also has internal heat, generated by radioactive decay in the core and residual heat from the planet's formation billions of years ago. That internal heat is gradually escaping through the crust, through volcanic activity, through geothermal vents. The Earth is cooling, slowly, imperceptibly on human timescales, but measurably over geological time. Billions of years from now, the Earth's core will have cooled significantly. The magnetic field may weaken or disappear. Volcanic activity will diminish. The planet will reach a thermal equilibrium with its surroundings. Not dead in the dramatic sense, just equilibrated, just evened out. This is the fate of every energy gradient in the universe. Every hotspot cools. Every concentration disperses. Every difference erodes. The sun is doing this right now. It radiates energy into space at a rate of about 3.8 times 10 to the 26th watts. That energy spreads outward in all directions as light, travelling through the solar system, past the planets, into interstellar space. Most of it misses everything. Most of it just keeps going, expanding into the void, its intensity decreasing with distance according to the inverse square law. A tiny fraction strikes Earth and powers nearly everything here: photosynthesis, weather, ocean currents, the water cycle. But even that energy eventually radiates back to space as heat. The Earth doesn't accumulate the sun's energy indefinitely. It uses it temporarily for processes that maintain the planet's far from equilibrium state, and then releases it. Every leaf that photosynthesizes absorbs sunlight and converts some of it into chemical bonds in glucose molecules. But the plant also heats up slightly from the light it can't use, and that heat radiates away. When the plant dies and decomposes, the chemical energy in its tissues is released by bacteria and fungi as they break down the organic matter. That energy becomes heat, which disperses. Even fossil fuels, which are concentrated stores of ancient sunlight, release that energy as heat when burned. The combustion converts chemical bonds into carbon dioxide, water vapor, and thermal energy. The thermal energy warms the air, powers engines, generates electricity, but ultimately it disperses into the atmosphere, into space. Nothing you do with energy prevents its eventual diffusion. You can transform it, concentrate it temporarily, use it to do work, but in every transformation, some portion becomes heat and disperses. And heat is the end state, the final form that energy settles into before it's too diffuse to extract work from. There's a term for this in thermodynamics: exergy, the portion of energy that's available to do work. As energy disperses, its exergy decreases. The total energy remains constant, but the useful portion shrinks. A hot steam boiler has high exergy. The steam can drive a turbine, generate electricity, do mechanical work. But once the steam cools and condenses, once the heat disperses into the environment, the exergy is gone. The energy is still there. The water molecules are still vibrating. But the difference between the steam and its surroundings has vanished. And without difference, without a gradient, there's no way to extract work. This is what the universe is doing. Not destroying energy, just erasing the differences that make energy useful. Diffusing it, spreading it, thinning it, until all that remains is uniformity and stillness, and the faint, even warmth of everything that once burned bright. You've felt this yourself, even if you didn't name it. The way warmth leaves. Step outside on a winter morning, and your body heat flows into the cold air surrounding you, your skin cooling rapidly as the thermal gradient between your 37-degree core and the freezing air drives heat transfer through conduction, convection, and radiation all at once. Your body fights back. Metabolism increases. Blood vessels in your extremities constrict to preserve core temperature. You shiver, generating heat through rapid muscle contractions. But you're fighting diffusion, and diffusion always wins eventually. If you stayed outside without shelter, without additional clothing, without a heat source, your body would gradually lose the battle against the cold, your core temperature dropping degree by degree until metabolic processes could no longer generate enough heat to compensate for the loss, until the difference between your body and the environment narrowed to nothing. This is why warm-blooded animals must eat constantly. Every calorie consumed is ultimately used to replace the heat that's continuously diffusing away from the body into cooler surroundings. You're not a closed system, you're an open system in constant energy exchange with your environment, maintaining your temperature only through perpetual import and export. Stop eating and the export continues without replenishment. the body cools. Diffusion claims what metabolism can no longer defend. But this isn't unique to living things, this constant need to import energy to maintain a concentrated state. Every ordered structure in the universe faces the same requirement. A building maintains its internal temperature through heating systems in winter and cooling systems in summer, both of which require constant energy input because the building is constantly exchanging heat with the outside air through walls, windows, roof, foundation. Turn off the systems, and the building's temperature drifts toward the outside temperature. In winter it cools. In summer it warms. The difference erodes without the energy input needed to sustain it. Your refrigerator does the same thing, running its compressor intermittently throughout the day to maintain the temperature difference between the cold interior and the warm kitchen, fighting the constant influx of heat through the insulation. The compressor stops, and warmth seeps in. The temperature rises. Food spoils not because energy enters the system, but because the system equilibrates with its surroundings, and that equilibrium is inhospitable to preservation. Equilibrium is the state where nothing interesting happens anymore, where all the gradients have flattened, where every region has the same temperature and density and composition as every other region. And the universe moves toward that state continuously, not through any active process, but simply because there are vastly more ways to be in equilibrium than to be out of it, vastly more configurations where energy is evenly distributed than configurations where it's concentrated. Random changes favor the common over the rare, equilibrium over disequilibrium, diffusion over concentration. Think about perfume in a room. You open a bottle in one corner, and the scent molecules begin to diffuse through the air, spreading outward from the region of high concentration near the bottle to regions of lower concentration elsewhere in the room. Within minutes, you can smell the perfume across the entire room because the molecules have distributed themselves more or less evenly throughout the available volume. But you never observe the reverse. You never see perfume molecules spontaneously gathering from throughout the room and concentrating back into the bottle. Not because it violates any fundamental law, the molecules could theoretically move that way, but because the probability of all those molecules randomly moving in coordinated directions to achieve that specific outcome is vanishingly small. There are billions of ways for the molecules to spread out, and essentially one way for them to concentrate back to the bottle. Random motion explores the space of possibilities and spends almost all of its time in the configurations that are common, that have many equivalent arrangements, that represent high entropy. This is why smells diffuse, why heat spreads, why energy disperses. Not because there's a force pushing toward dispersal, but because dispersed states vastly outnumber concentrated states in the space of all possible configurations. The universe doesn't prefer equilibrium in any intentional sense. It just explores configuration space randomly and ends up in equilibrium because that's where most of configuration space is located. It's like dropping a marble into a landscape of hills and valleys. The marble rolls downhill, not because downhill is special, but because there's more low elevation than high elevation, and gravity pulls the marble toward regions of lower potential energy. Similarly, isolated systems drift toward high entropy configurations, not because high entropy is preferred, but because high entropy states are statistically dominant. And energy dispersal increases entropy because spreading energy among more particles creates more possible ways to distribute that energy, more microstates compatible with the same macrostate. When a hot object touches a cold object and heat flows from hot to cold, the energy that was concentrated in the fast-moving molecules of the hot object gets distributed among both the fast-moving and slow-moving molecules of both objects. The total number of ways to arrange that energy among all the available molecules increases dramatically. The system can now access far more microstates than it could when the energy was concentrated in just one object. That increase in accessible microstates is entropy increasing. And it's irreversible, not because the reverse violates physics, but because the reverse is so improbable you'd have to wait longer than the age of the universe to see it happen by chance. The heat could spontaneously flow from the cold object back to the hot object if all the relevant molecules happen to be moving in exactly the right directions at exactly the right moments. The math allows it, but the odds are astronomically against it, so in practice it never happens. Heat flows from hot to cold. Energy disperses from concentrated to dilute, and time marches forward. This is the deep connection between energy dispersal and the arrow of time. Time flows in the direction of increasing entropy, in the direction of energy spreading from concentrated sources into diffuse surroundings. And every process you observe, every change you experience, every event that unfolds in your life is a small manifestation of this universal tendency. Your morning coffee cools because time flows forward. The sun radiates energy into space because time flows forward. Stars age and galaxies evolve because time flows forward. And time flows forward because energy disperses. And energy disperses because dispersed states are more common than concentrated states. And concentrated states evolve toward common states because random changes favor the probable over the improbable. It's a loop of causation that doesn't have a beginning or an end, just a consistent direction. Forward. Always forward. Toward diffusion. You're participating in this right now as you lie here listening. Your body is radiating heat into the cooler air and mattress around you, infrared photons leaving your skin and being absorbed by nearby surfaces. The blanket slows this process by trapping a layer of warm air close to your body, reducing the temperature gradient between your skin and the environment, but the heat still leaks out, eventually, through the blanket's fibers and into the room. You're losing energy constantly, replacing it constantly through metabolism, maintaining your concentration against the universe's tendency to diffuse. And when you sleep deeply, your metabolic rate decreases slightly, your body temperature drops a fraction of a degree, and you drift closer to equilibrium with your surroundings, without ever quite reaching it as long as you're alive. Life is a sustained resistance to equilibrium, a continuous import of low-entropy energy in the form of food and sunlight, and a continuous export of high-entropy waste in the form of heat and exhaled gases and excreted compounds. You maintain your organization, your structure, your warmth, by accelerating the universe's overall march toward disorder. You create local order at the expense of greater global disorder. You concentrate energy temporarily, while dispersing even more energy permanently into your environment. And this is true of everything alive, every cell, every organism, every ecosystem. A forest absorbs sunlight and converts some of it into the chemical bonds of wood and leaves and roots, creating concentrated stores of energy that persist for years or decades. But the forest also radiates enormous amounts of heat from its canopy, releases water vapor that carries latent heat into the atmosphere, supports decomposition that releases carbon dioxide and heat back into the environment. The forest concentrates some energy while dispersing far more. The net effect is increased entropy, increased diffusion. Even the process of photosynthesis, which seems to create order by building complex molecules from simple ones, increases the universe's total entropy, because the sun had to disperse vast amounts of energy into space to provide the concentrated photons the plants captured. For every joule of chemical energy stored in a glucose molecule, many joules of solar energy scattered into the void as the sun radiated in all directions. The local decrease in entropy is dwarfed by the global increase. And this is why life doesn't violate the second law of thermodynamics, even though living things clearly create order and complexity. They create it by coupling to an even larger source of disorder, the sun, which is itself dispersing energy from its hot core into cold space. The sun is burning through its fuel, fusing hydrogen into helium, releasing energy in the process. And that energy spreads outward at the speed of light, thinning with distance, warming planets briefly before continuing into the darkness beyond. The sun has been doing this for 4.6 billion years and will continue for another 5 billion or so before it exhausts its hydrogen fuel and transitions to burning helium, swelling into a red giant, engulfing the inner planets, and eventually shedding its outer layers to become a white dwarf. That white dwarf will cool over trillions of years, radiating its residual heat into space, gradually approaching the background temperature of the universe, diffusing, equilibrating, fading. And long after the sun is gone, long after every star has burned out, the energy that once concentrated in stellar cores will be spread throughout the universe as low-temperature thermal radiation, still there, still conserved, but no longer capable of driving any process or creating any change or supporting any life. Just background warmth, just diffuse existence, just the faint glow of everything that once shone. And in that distant era, if time still has meaning, if there's still something to mark the passage of moments, the universe will rest. Not empty, not dead, just equilibrated. Just finally, completely, evenly diffused. The cosmos is patient, unimaginably patient, and what it waits for, without intention or awareness, is the gradual evening out of every difference that exists, each one containing hundreds of billions of stars, and those stars pour energy into the void through radiation that will travel for eons before encountering anything capable of absorbing it. Most of that radiation just spreads. It expands with the universe itself. Its wavelength stretches as space expands, redshifting toward lower and lower energies. Light that left a distant galaxy as ultraviolet might arrive at Earth as infrared. Light that left as visible might arrive as microwave radiation. The photons lose energy not because anything absorbed it, but because the space they're traveling through is expanding beneath them. That expansion dilutes the radiation. The same number of photons spreads across an ever-increasing volume. Density decreases. Intensity falls. The universe itself is a diffusion mechanism. Within galaxies, stars cluster together, gravitationally bound. But even those clusters are temporary on cosmological timescales. Stars orbit the galactic center, occasionally passing close to other stars, occasionally being ejected from the galaxy entirely by gravitational interactions. Over hundreds of billions of years, galaxies will disperse their stars. Not through explosions or violence, but through the slow accumulation of small gravitational nudges that eventually send stars on trajectories that carry them far from where they formed. The galaxy becomes less dense, less concentrated, more diffuse. And between galaxies, in the vast voids that make up most of the universe's volume, there's almost nothing. Intergalactic space contains perhaps 1 hydrogen atom per cubic meter on average. That's a better vacuum than anything humans can create in laboratories. And it's getting emptier. As the universe expands, the distance between galaxy clusters increases. The voids grow larger. The matter that exists spreads across more and more space. Eventually, galaxies will be so far apart that an observer in one galaxy won't be able to see any others. The light from distant galaxies won't have enough time to reach them before the expansion of space carries those galaxies beyond the observable horizon. Each galaxy will be alone in its own bubble of visible universe. Isolated, surrounded by darkness. But even within an isolated galaxy, diffusion continues. Stars burn out. White dwarfs cool. Neutron stars radiate away their rotational energy and slow to stillness. Black holes evaporate through Hawking radiation. Hawking radiation is the ultimate diffusion process for concentrated mass energy. Quantum effects near the event horizon of a black hole allow particle-antiparticle pairs to form, and occasionally one particle falls into the hole while the other escapes. The escaping particle carries energy away from the black hole. The black hole loses mass. Slowly. Unimaginably slowly for large black holes. A solar mass black hole would take 10 to the 67 years to evaporate completely. A supermassive black hole, like the one at the center of the Milky Way, would take 10 to the 100 years or longer. These timescales dwarf the current age of the universe by factors too large to comprehend. But they're finite. Eventually, every black hole evaporates. And when they do, the mass energy that was once concentrated in a singularity, compressed to infinite density, would have dispersed as radiation across the entire observable universe. Diffused, scattered, thinned beyond any possibility of reconcentration. At that point, trillions upon trillions of years in the future, the universe will contain only radiation and perhaps some stable fundamental particles like electrons and positrons, all of them spread so thinly that interactions between particles become vanishingly rare. The temperature of the universe will approach absolute zero asymptotically, not reaching it because absolute zero is unreachable by the third law of thermodynamics, but getting arbitrarily close. All energy will be diffused, all differences erased, all gradients flattened. This is heat death. Not death in the sense of destruction, but death in the sense of cessation. Nothing happens anymore because there's no difference to drive processes, no hot and cold, no dense and sparse, no motion that leads anywhere. Energy still exists. The total amount is conserved, but it spreads so evenly across such vast distances that it's no longer capable of doing work or creating structure or supporting complexity. The universe reaches maximum entropy, the state where disorder is complete, where organization is impossible. And in that state, time loses meaning, because time as we experience it is the perception of change, of events following one another, of systems evolving from one state to another. But in maximum entropy, nothing evolves, nothing changes. The universe just exists, static and uniform, with no arrow pointing from past to future because there's no difference between past and future. Every moment is the same as every other moment, indistinguishable, eternal. This future is certain. Not soon, not in any time frame relevant to human concerns or even to the lifespan of stars, but inevitable. Unless something intervenes that we don't yet understand. Some undiscovered physics, some process that concentrates energy on cosmic scales, some mechanism that reverses entropy locally without increasing it globally. But no such mechanism is known, and every observation confirms the trend. Energy disperses. Entropy increases. The universe expands and cools. The direction is clear. But here, now, tonight, the universe is still young, still full of stars, still structured, still capable of complexity and life and thought. You exist in a brief window, cosmologically speaking, when the universe has cooled enough from the Big Bang to allow stable atoms and molecules and chemistry, but hasn't yet cooled so much that all the stars have died. A window that will last for perhaps 100 trillion years total. We're 13.8 billion years in. Early in the window. Still in the era when galaxies shine. Still in the era when diffusion is local rather than universal. When energy still concentrates in pockets even as it disperses overall. Your body is one of those pockets. A temporary concentration maintained by continuous energy flow. Food enters. Heat exits. You persist in the gap between those flows. But the gap is temporary. It lasts a human lifetime. Maybe 80 or 90 years if you're fortunate. Then the flow stops. The concentration disperses. The atoms that made up your body return to the environment. Carbon to the air. Calcium to the soil. Hydrogen to water. Iron to rust. The energy that animated those atoms, the warmth, the motion, the electrical signals in neurons, disperses as heat into the surroundings. Not lost. Never lost. Just redistributed. And those atoms will likely become part of other structures eventually. Other organisms. Other molecules. Cycling through Earth's biosphere and geosphere for billions of years until the sun expands and sterilizes the planet. Then they'll be part of the expanding gas cloud as the sun sheds its outer layers, dispersing through interstellar space, joining the diffuse matter between stars. Still there, still real, but no longer concentrated enough to form anything complex. This is the fate of all matter, all energy, all structure. Not annihilation, just diffusion, spreading, thinning, returning to the background. And the background is patient. It has all the time that exists, all the space that expands, all the capacity to absorb what was once concentrated. It waits, without hurry, without preference. And one by one, everything that concentrates eventually disperses into it. Stars into radiation, planets into dust, dust into atoms, atoms into particles, particles into fields, until nothing remains concentrated anywhere, until the universe is truly uniform, truly equilibrated, truly at rest. But not tonight, not for eons, not while stars still burn and planets still orbit and life still persists. Tonight there is still warmth, still difference, still the possibility of change, still you, still here, still warm against the cooling night, still resisting, still concentrating, still alive. There's a question worth sitting with as this draws to a close. Not a question that demands an answer, but one that opens into quiet contemplation. If energy never dies, only disperses, what does that mean for everything you've experienced? Every warm conversation, every moment of sunlight on your face, every meal that nourished you, every thought that passed through your mind. All of it involved energy transformations. All of it took concentrated energy and dispersed it. All of it left traces in the universe that still exist, just scattered beyond recognition. The warmth of a hug you received years ago, that thermal energy transferred from another person's body to yours. You radiated it away within hours. It's in the air now, mixed with everything else. But it's still there. The light that illuminated your childhood bedroom, photons from a bulb or the sun that struck your retinas and allowed you to see. Those photons were absorbed, their energy converted to electrical signals in your neurons, then to heat as your brain processed the information. That heat dispersed from your body, into your pillow, into the air, into the night. Every experience you've had left an energy footprint. Every step you've taken, every word you've spoken, every tear you've cried. And all of that energy is still part of the universe, Not gone, just transformed, just spread. This doesn't mean your experiences are preserved in any recoverable way. The information is lost, scrambled by the countless interactions that dispersed the energy. You can't reconstruct a memory from the thermal vibrations of air molecules, but the energy itself persists. The actual joules that powered those moments, they exist. Somewhere. Everywhere. And this is true not just for your personal history, but for all of history. The energy that powered ancient civilizations, that lit medieval candles, that drove the Industrial Revolution, all of it dispersed into the environment, all of it now part of the thermal background of Earth's atmosphere and oceans. The universe is an archive of everything that has ever happened, but it's an archive written in a language of dispersed heat that cannot be read. The information is there in principle, the energy is conserved, but the organization is lost. The structure has dissolved into randomness. This is the price of time flowing forward, the price of entropy increasing. The universe remembers the total amount of energy, but forgets the details of what happened with it. And perhaps that's appropriate. Perhaps perfect memory would prevent change. Perhaps forgetting, in the thermodynamic sense, is what allows the universe to continue evolving, rather than being trapped in its past configurations. Perhaps dispersal is a kind of release. You release heat constantly. Every breath, every heartbeat, every thought. You're not holding on to the energy that flows through you. You're letting it go. And in letting it go, you allow new energy to enter, new food to be metabolized, new experiences to unfold, new moments to exist. Life is a continuous flow, not a static accumulation. Energy enters, energy exits. You exist in the pattern of that flow, not in any fixed amount of energy that stays with you. The atoms in your body now are not the same atoms that were there 7 years ago. They've been replaced through eating and drinking and breathing and shedding. You're a pattern that persists through continuous material exchange. A concentration that maintains itself by allowing flow. A temporary resistance to diffusion, but only temporary. Eventually the flow stops. The pattern dissolves. The concentration disperses. And the energy that was you returns to the environment, not as punishment, not as loss, just as the natural conclusion of what it means to exist in a universe where energy spreads. You were always borrowing the energy, always just holding it briefly, always destined to return it. And that's true of everything. Stars borrow energy from gravitational collapse and fusion. Planets borrow energy from their formation and radioactive decay. Ecosystems borrow energy from the sun. All of it temporary. All of it flowing. All of it ultimately dispersing. The universe is generous in this way. It allows temporary concentrations. It permits local decreases in entropy as long as the total increases. It enables life and complexity and consciousness. But it doesn't allow permanence. Everything that concentrates will eventually disperse. Everything hot will cool. Everything ordered will mix. Everything bright will fade. Not because the universe is cruel, but because dispersal is the most probable state. Because spread configurations vastly outnumber concentrated ones. And so the universe drifts toward diffusion. Not through intention, not through design, just through the mathematics of probability. And we drift with it. But not passively. While we exist, while we maintain our concentration, we participate in processes that create temporary islands of order. We think. We build. We love. We make meaning in the brief window before diffusion claims us. The universe doesn't require this meaning. It would proceed toward heat death with or without our efforts. But we create meaning anyway. Because we can. Because we're here. And in creating meaning, we use energy. We concentrate it briefly in neural patterns, in relationships, in structures. We take some of the universe's diffusing energy and organize it into something that matters to us. For a while. Then we release it. Back to the diffusion. Back to the background. Back to the patient, expanding cosmos that will eventually absorb everything. This is not tragedy. This is just physics. Just the way energy behaves in a universe with these particular laws. And within these laws, you exist. Temporarily concentrated, briefly warm, momentarily organized, making meaning while you can, living while you can, resisting diffusion while you can, until you can't. And then you'll return to the flow, to the dispersal, to the background from which you temporarily emerged. Your energy will spread. Join the oceans. Join the atmosphere. Join the radiation that fills space. Still there. Still conserved. Still real. Just no longer you. And that's the answer to the question. Energy doesn't die. It doesn't vanish. It doesn't end. It just diffuses, spreads, thins, mixes with everything else, until it's everywhere and nowhere at once. The universe holds it all. Every joule that ever concentrated, every bit of warmth that ever existed, spread now across infinite distance, thinned beyond recovery, but never destroyed, never lost, just returned, just released, just diffused, back to the quiet, back to the stillness, back to the gentle, even warmth of everything, everywhere, at rest. Thank you for spending this time here tonight, for letting these ideas settle into the quiet spaces of your mind. If this brought you any rest, any calm, any gentle understanding, consider sharing it with someone else who might need the stillness. A like helps others find their way here. A subscription means you'll return when you need this again. And that's all. Just an invitation to rest, to let go, to allow the day's energy to diffuse into the night. Sleep well. Let everything settle. The universe will hold it all.